Hey, this is a fun episode. Projectile motion. We're going to spend 2 days at this. First off, just for a bit of context, there was this famous show called Mythbusters where they wanted to prove this, that if you fire a bullet and you let it drop, if you place it in the right spot where the bullet drops, hits the ground, the bullet will hit it at the same time. After all, they're both succumb to the force of gravity. Right? So they both start at the same height and they will collide at the same spot, like in this animation right over here. So they sat down, they did all the preliminary math, they calibrated their equipment, and how about, well, let's do a physics teacher reacts video.
And a victory for physics.
So that poses a question, a very good one. Is 39.6 milliseconds the same thing as 0 seconds? Well, let me put it to you in a different context. Let's say that we didn't use the unit of seconds and we used the unit of years. Does that mean that a 40-year-old man is the same age as a newborn baby? And now you'll see what I mean, all right? I know the show is trying to rush through it and get to the point of it all, so it doesn't really emphasize much about significant figures and uncertainty. All measurements have an uncertainty, because without the uncertainty, the number is completely meaningless. So if in this experiment that they conducted that they had an error margin of roughly 40 milliseconds, then yeah, arguably speaking, 39.6 milliseconds is within the error margin, so therefore it's the same as 0. But without that blanket, that safety blanket of the uncertainty, no, 39.6 is not the same as 0. Okay, so whenever you're doing your experiments, always include an uncertainty in your calculations. It's very important in your research. We'll save that for first year university though. Okay, as for now, let's just deal with the fun joys of projectile motion. All right, and another way of seeing how things work out is imagine this. All right, that you're chewing gum while riding a bicycle. You tilt your head upwards, and you spit the gum upwards, but you're still riding forwards, like in this animation right over here. Believe it or not, no matter how fast you're riding the bike or how slowly you're riding the bike, as long as you're maintaining uniform motion traveling the same direction, the bubble gum will always fall back into your mouth again. It sounds rather trippy. And the reason why this works out is because both the gum and you share the same exact horizontal velocity. All right. So even though the vertical velocity of the bubble gum may change during its entire projectile motion, the horizontal component is matched dollar with you and your bicycle. So that's why every time it'll always fall back into your mouth again. This is a great way of emphasizing how these two universes are independent of each other or orthogonal. Orthogonal just simply means 90 degrees to each other. In other words, whatever you do this way, it has no impact this way. All right? Because no matter how fast you run backwards or forwards, you're never going to get to the stars. And no matter how high or how low you jump, you'll never get it to the emergency exit on the far side, if you know what I mean. All right. So yes, those two dimensions are independent of each other. So that's part of the secret sauce of solving these problems. You solve the horizontal problem with respect to time. You solve the vertical problem with respect to time. The time it takes for the ball to go up and down is the same exact time it takes for the ball to travel all the way across. All right. So gravity only impacts the vertical dimension. So you know for sure AY is equal to negative 9.81 meters per second squared down. We're going to pretend that the air resistance is not a thing, because if air resistance was a thing, then yes, you'd be slowing down as you're moving horizontally. But for the purposes of high school physics, we always assume that AX is equal to 0. Okay? In other words, your Vx remains constant. So there is no Vix and Vfx, it's just Vx. All right? But your y value will change. You might slow down as you go up and speed up as you go down. Time remains the same in both dimensions. Just due to the concerns of copyright, I'm not going to bother showing that video, but it's just emphasizing the whole bubblegum demonstration. All right, so let's go through 2 examples today. Here's the first one. If a ball was thrown at 40 meters per second forwards off the top of a 100-meter tall cliff, how far will it land from the base of the cliff? Once again, if gravity didn't exist, the ball would just travel horizontally forever. And if you were to drop the ball, it would drop due to the influence of gravity. But combine them together, and that's what the curve of a projectile path really is. A uniform component horizontally and a quadratic component in the vertical dimension. So how would you solve this problem here? There's many different ways of doing it. Some people like to do givens and do a whole entire givens chart. All right, it would look something like this. I'm just drawing it really crudely. You have your delta dx, you have your delta d, your delta d, your vi, your vf, your a, and then your delta t, which once again it remains the same in both dimensions. Then you have your x and y components, which you're going to fill in like crazy. And if that works for you in your organization, because many tutors teach it this way, go ahead and stick with it. I'm fine with that. However, the way how I would do it is that I would just do two separate sets of givens and work through it independently. All right, like so. So in my x dimension, we know that ax is equal to 0 meters per second squared. Do you need to write that out? No, you don't have to. All right. But in this case over here, you notice that you do have a Vx, which is 40 meters per second forwards. And if you're shooting it just forwards, that means that there is no y component, right? Because it's kind of like me letting go of something. The moment I let go of something, it starts off at 0 meters per second before it accelerates. All right, so your Vi, y, is equal to 0 meters per second. How far do you travel horizontally? You don't know yet, but you do know that the object does fall 100 meters down. Okay, so in the x dimension, you don't have enough information to solve for. You don't know time, you don't know, you don't know time, so you can't solve it. It's impossible. So we have no choice but to solve for the y dimension. All right, after all, that's the only thing that you have at least 3 givens. So in this case over here, you'll probably want to pull out the third kinematic equation. Delta d is equal to vi delta t plus 1/2 a delta t squared. And luckily for us, because this term over here goes to 0, this formula is actually fairly straightforward to rearrange and solve for. It's not too bad. Sub all the values in, crunch it through, and this is the amount of time it takes for it to fall. 4.5 seconds. Well, if it takes 4.5 seconds for it to fall, then it must also take 4.5 seconds for it to travel across at the speed of 40 meters per second. So you'll multiply the 4.5 seconds by 40 meters per second, and that'll get you to your final answer. That's it. Again, this is one of the easiest problems. Don't expect to have a question this straightforward on a test or on an exam, but this sets up the foundation of how we solve all projectile problems. After all, with projectile problems, you're trying to project it. You're trying to launch it at an angle. You're not just trying to shoot it horizontally every single time. So that's what we're going to do. We're going to angle the ball at, let's say, at an angle of 30 degrees above the horizontal. Like so. Okay, and whenever you're solving these problems here, what you want to do is that you want to draw out a brief sketch. Okay, usually I like to draw a brief sketch that looks kind of like this. All right, but I don't have that out here on my PowerPoint. So with regards to this projected angle has two components. It has its horizontal component and it has its vertical component. And you probably want to take the time in breaking down these right now. All right, so you know that your Vx, which will always remain the same, is equal to the hypotenuse times, well, that's beside 30 degrees or adjacent, so cosine of 30 degrees. As for your Vy, remember it's going to slow down till it reaches the top, then speed up. So you can't just call this Vy. You have to call it Viy, because it's the initial y value going upwards. It will decrease and increase again throughout its entire projectile path. This is equal to the hypotenuse times the opposite of 30 degrees. So you sit down and crunch through all this stuff on your own, and usually these are 2 marks right here for breaking down your projectiles into its components. Next, we'll group them all out together and start solving the rest of this. All right, you'll notice that you'll have to solve first for your vertical calculations because you know how far it's going to drop. You have your delta dy. You also know its y component for its Viy. And lastly, acceleration is pulling it down. All right, so from before, we calculated out our Viy to be 20 meters per second. Your Ay is at negative 9.81 meters per second squared. And this ball launcher is located 100 meters above. So it's going to fall 100 meters down. That's why there's a minus sign there. Okay, if you assume upwards as positive. That's important. It's a common mistake a lot of students make. They forget that if it falls, it's going to be negative. All right, because there are times where you launch things, and let's say you want to land on a bookshelf up above. then you're going to have a positive dy. All right, so anytime that you have your vi, a, and delta d, you can solve for time using the third kinematic equation. And here's where things get a little messy, because the moment you sub everything in, you calculate through it, you'll notice that you'll have something that's quadratic, something that's linear, and something that's a constant. In other words, you have this whole a squared plus b squared plus c, sorry, a squared plus bx plus c is equal to 0. All right, where you have to use the quadratic formula in solving it. And yes, with the quadratic formula, you're going to end up with two answers. You're going to have a positive root and a negative root. Not always, but in this case over here, you will. I don't want you to ignore the -1, but you know that logically speaking, there's no such thing as negative time. So you probably cross out the -3 seconds. That doesn't make any sense. And you'll take 7 seconds as your valid answer. All right. So yeah, it took 7 seconds for it to go up and all the way down. So if it had 7 seconds to go up and down, it also bought itself 7 seconds to travel across. So going back, we've already calculated out the horizontal component of our velocity, 34.64 meters per second. So 34.64 meters per second times the 7 seconds will give us our horizontal range. All right. Horizontal range by definition is how far does it travel from the base of the cliff to its end destination. That's its range. Before we move forwards, I do want to emphasize something. This minus sign over here, what exactly does it imply? Well, here's the crazy thing. If you were to start the experiment 3 seconds before, and you throw the ball so hard that by 3 seconds, you'll make it to the 100-meter mark, remember, you just modeled a curve that looks like that of a parabola. And if it models that of a parabola, then the rest of the parabola would follow that exact shape. All right. So these kinematic problems, some of them are based upon the quadratic formula. That's why it's going to have two roots. But from us as human beings, we know there's no such thing as negative time. That's why we ignore it. All right, or we drop it out. I don't want you to just drop numbers just because they're minus. I want you to think about logically why it's true. All right, before you end up dropping it. And here's the reason behind it. You can technically start the experiment 3 seconds before, throw it so hard that by 100 meters, it's already at that starting point, and it's going to follow the same exact path as if you launched the ball from up on that cliff. There will be no visible difference. Okay, so our last question is, well, what is its impact velocity? Now, if you're looking for impact speed, then direction doesn't matter anymore. But in our universe of kinematics, we're looking for something that has direction. So let's go figure that out. As mentioned with regards to this projectile over here, the horizontal component remains the same throughout the entire journey. So that doesn't change. All right, so our Vx, is equal to 34.64 meters per second. That hasn't changed. But our y component has changed. So how fast is it falling at the 7-second mark? You could use the 7 seconds, but if you made a mathematical mistake in getting to your 7 seconds, you're going to carry the error through even more. All right. So you probably just want to stick with the values that you know of from before. In other words, your VIY, your AY, and your delta D. These are the same givens as in the previous slide, except that this time around, instead of solving for time, we're solving for VFY. You pull out that last kinematic equation, sub everything in, and yeah, technically speaking, when you solve this, since you have to square root both sides, you have a plus and minus. All right, and we'd take the negative as our logically correct answer. After all, with this parabola over here, as things are going to be symmetrical, if this is falling downwards at, what was that number? I should have copied it down in my head. 48.6 meters per second. If this had a slope of 48.6 pointing downwards, then over here, this should have also the same slope of 48.6 upwards. It is a parabola, so it must be symmetrical there. And that's why you're going to have this positive and negative answer. Well, we're not really concerned about launching it upwards, and that's why we're dropping the positive solution. The negative solution only makes sense for our problem here. Okay, so now we have a problem or a solution where we know the adjacent and the opposite hypotenuse can be solved by using, yet again, the Pythagorean theorem. Beautiful. Angle can be solved by using inverse tangent. And that's it. So this is part 1. Go through these questions tonight, and we'll move on to more challenging examples in tomorrow's lesson. See you then.